Good day, everyone. My name is Narenthiran, son of Murukan. Today, me and my project team members are excited to present our project, EcoSort Automated Household Waste Classifier. This project was developed by Chee, Narenthiran, that's me, Zhee Ying, and Zhee Yee. We designed EcoSort as a highly accessible browser-based solution to address one of the most persistent environmental challenges today: improper household waste segregation and general lack of clear recycling guidance. Utilizing an optimized mobile net transfer learning architecture via TensorFlow JavaScript, our system is capable of instantly identifying 6 key categories of household waste, which is plastic, paper, glass, metal, organic, and general trash, achieving an overall classification accuracy of 85.6% directly inside a standard web browser. Our ultimate goal with EcoSort is to put a frictionless, privacy-first tool into the hands of everyday consumers, helping households minimize recycling errors and directly aligning our communities with the United Nations Sustainable Development Goal 12 for responsible consumption and production. To understand why we built EcoSort, we first have to look at three core problems in waste management today. The contamination cascade. It all begins with the household confusion. Everyday consumers genuinely want to recycle, but they lack clear, immediate guidance on how to properly categorize their daily waste. This confusion leads to directly stream contamination, where recyclables are mixed with general waste, spoiling clean and viable materials like paper and cardboard. When these contaminated streams arrive at material recovery facilities, they cause severe processing inefficiency, forcing manual sorting demands and driving up operational costs. Ultimately, this leads to a massive environmental impact. Tons of perfectly usable materials are diverted right back into landfills, failing our unsustainable development goal 12 objective. EcoSort is designed to disrupt this exact chain reaction right at the resource. Our solution to this problem is built on three core pillars that define the EcoSort paradigm. First, real-time guidance. EcoSort provides instantaneous visual classification across 6 common household waste categories to intercept contamination the exact moment a user is about to throw something away. Second, we prioritize zero friction access. The platform is built entirely on native web technologies like HTML, CSS, and JavaScript. This means there is absolutely zero app installation required. It extends our reach to any standard webcam activate device instantly. Third, and perhaps most importantly, is privacy-first execution. Webcam streams never leave the user's device. By utilizing TensorFlow, all AI processing occurs entirely within the local browser session, ensuring user data is never compromised. Now let's pull back the curtain and look to our end-to-end operational framework to see how a single frame transforms into actionable recommendation. The pipeline consists of 4 sequential stages. First, image acquisition. We initialize the webcam via the browser's media devices API to capture raw pixel data in real time. The second is pre-processing and normalization. The raw matrix is spatially downsampled to a fixed 224 by 224 pixel matrix to match our model. We then apply a mathematical normalization formula to the pixel intensities to ensure numerical stability. The third one is classification inference. The normalized tensor is processed right through our locally hosted mobile net neural network, which outputs a probability distribution across our 6 target categories. Then the fourth is recommendation generation. Finally, if the dominant category passes our strict 75% confidence threshold, it maps to a structural rule engine, outputting immediate practical disposal guidance to the user interface. To wrap our architecture overview, let's look at why this browser-native approach gives us the client-side advantage over traditional cloud AI. Traditional cloud systems rely on external servers, which introduce high latency, require persistent databases, and create significant privacy risks. EcoSort completely flips this model in 3 major architectural wins. The first is zero server cost. We bypass expensive ongoing cloud processing servers entirely, allowing the applications to scale freely. The second one is zero latency. By eliminating the network round trip time, we achieve smooth real-time video frame analysis. And then the last but not least, maximum privacy. Because raw images matrices are analyzed and discarded locally. No user data ever permanently stored or transmitted over the internet. That's all from me.
Hi guys, I'm Chloe. I will explain category of our AI model can recognize. Our system classifies household waste into 6 categories, which are glass, plastic, paper, cardboard, organic waste, metal, and trash. For glass, it includes items like bottles and jars that are transparent or tinted and usually have shiny reflection. Plastic include things like plastic container, bag, packaging material. They usually have smooth surface and regular shape. Paper and cardboard include newspaper, paper sheet, and box made from cellular fiber. Organic waste refer to food scrap and other biodegradable material. These usually have irregular shape and earthy color. Metal include aluminum can and steel container, which are easily to identify because of their metallic shine. Finally, we have the trash category. This is basically the default category for non-recyclable items like used tissue and dirty material that don't fit into the other recyclable thing stream. Next, to train our model, we collected a total of 7,830 training images using teachable machine and also real-world image capture. We wanted the dataset to be realistic as possible, so we can include different conditions. First, we use different lighting environments such as bright indoor lighting, natural daylight, and deep condition. Second, we capture objects from different angles, include tighter, upright, and top-down view. Third, we use different background like kitchen table, outdoor floor, and recycling bin. Lastly, we make sure there was morphologic diversity, meaning objects within the same category could have different shape, size, and color. This helped our model become more robust and perform better in the real-life situation. Before the image going into the AI model, it needs to go through processing. First, every image is resized into a fixed size of 324 by 324 pixels. This ensures that every image have the same dimension before entering the model. Next, the pixel value are normalized. Normally, image pixels value range from 0 to 255. We transform them into value between -1 and +1 using this formula. The reason we do this is because MobileNet was originally trained use normalized input. Normalization improve numerical stability, make the learning process more efficient, and ensure consistent input data from the model. After processing, the image is sent into MobileNet, which is the pre-trained model we used for our project. MobileNet was originally trained on around 1.2 million images from the ImageNet dataset, so it already know how to recognize general features such as shape and texture. In our project, we use MobileNet as the feature extractor and keep it pre-trained wet frozen. Then we add our own desk classification layer that is specifically trained to recognize our 6 waste categories. MobileNet also use something called deep waste spreadable convolution, which significantly reduce computational complexity. Because of this, our system can run efficiently inside the web browser with low latency. Finally, the softmax layer produce probability score for all 6 classes, and the class with the highest probability become the final prediction. That's all. Thank you.
Let's look at how EcoSort filter is predation to ensure reliability. We have our own validation gate. The system does not just display a guess. It evaluates the module softmax output against a strict 75% confidence threshold. Pass strict if the confidence score is above 75%, the recommendation is immediately displayed to the user. But when it is fall below 75%, the system automatically flags it as unverified and prompts the user to recapture the image. This filter is essential for handling real-world variables like motion blur, poor lighting, or background interference, preventing the system from giving incorrect disposal advice. An image passed that gate, it triggers a specific actionable recommendation. We see our intelligent recommendation mapping, which Bridge AI classified with direct user action. For plastic, route to the plastic bin, instruct user to rinse container and flatten bottom for safe place. For paper, route to the paper bin, advise keeping it dry and flattening cardboard boxes. For glass, route to glass bin, warn user not to wrap it in a paper or mix it with ceramic. For metal, route to a scrap processor, instruct user to crush can and separate steel from aluminum. For organic, route to the compost heap, request zero packaging and draining liquid waste first. By giving clear instruction, we eliminate households confusing at the source. Now let's look at the actual performance data behind its mapping. From this slide is displayed our performance evaluation dashboard. Evaluated against a balanced test set of 300 images, EcoSort achieved an impressive overall accuracy of 85.6%. Top performance is metal, lead at 19% accuracy, following by plastic at 88%. This material have highly consistent visual features like metallic sheen and uniform shape. Next is solid baseline, which is paper and glass both achieve 86%. The lower performance is organic and trust set at 82% due to their inherent high visual variability. Overall, this proves our lightweight Bowers native model is highly capturable. To improve this accuracy further, we analyze the actual root cause of our area. In this slide, our area root cause analysis highlight the two primary areas of confusion. First is organic versus trust, which has 37% of areas. This occurs primarily when organic food scraps are enclosed in plastic or paper packaging, confusing the filter extracted. The second one is plastic versus glass, which has 28% of area. This is caused by specular reflectance overlap, where strong lighting on smooth plastic container create refraction that mimic glass.
Everyone, my name is Zhee Yee, and today I'm going to continue about our project-based presentation about project synthesis, viability, and impact. To synthesize our findings, EcoSort operates as a highly viable, freely accessible public utility that directly drives United Nations Sustainable Development Goal 12 for responsible consumption and production. Our project success balance perfectly across three core pillars shown on this framework. First is accuracy, backed by mobile net transfer learning. Our model achieved a strong 85.6% accuracy rate, providing it is highly capable of parsing complex, real-world visual environments. And the second is accessibility. This is also zero install. By designing a browser-native UI, which is user interface, we have achieved zero install friction, ensuring immediate availability of any web-capable household device with a camera. And the last one is cost and privacy, which is field server. Because TensorFlow.js executes entirely within the local browser session, we eliminate ongoing cloud hosting or server infrastructure costs while guaranteeing maximum data privacy for the user. Next, looking ahead, we had outlined a strategic four-phase roadmap to expand EcoSort capability and reach. Phase 1, focus on dataset augmentation. We will target our current 82% accuracy bottleneck by specifically collecting edge case images of composite materials and challenging organic to trash intersection. Phase 2, introduce taxonomy expansion. We plan to introduce new, highly impacting identification classes including electronic waste, hazardous household chemicals, and also construction waste. Phase 3, multi-class detection. We will upgrade from single label image classification to object detection, bounding boxes, allowing the system to identify multiple mixed materials with the exact same frame. Last but not least, Phase 4, target CF-Lite deployment. We aim to develop a lightweight native mobile application using TensorFlow Lite to provide enhanced portability and seamless functionality in varied offline environments. And that's all for our presentation. And now I'm going to demonstrate our EcoSort garbage classifier using objects that are not fed to AI during learning process. So we have to click Start Webcam to start this application. After clicking the Start Webcam, they will have a pop-up to ask for webcam permission. Since we didn't create a neutral category, so it will simply identify what's in the cam to random category. For this case, it is identified to paper and cardboard category. And now I'm going to demonstrate our application using glass. So as you can see, the application has 100% confidence that the item is glass and give a recommendation that place in the glass recycling bin. The next item we're going to demonstrate is metal cup. As you can see, the metal cup is identified in the metal category and have a recommendation that is to drop into the metal recycling bin. And the next item we're going to demonstrate is organic, which is food. And in this case, we're using a biscuit. So you can see the application has 100% confidence that the item is organic classes. Next, I'm going to demonstrate with paper and cardboard using a paper. So the application still have 100% confidence that it is a paper and recommendation to place in a paper or cardboard recycling bin. Next is plastic. This is a plastic bottle and the application has 100% confidence also that this is a plastic category and have a recommendation also. Last but not least is trash. So we have a category our shirt in trash category and the application have 100% confidence that it is a trash category and the recommendation also. That's all from us. Thank you.